Hello, welcome to our next chapter where we will be talking about liquid-liquid solutions. Now what we mean by this is we're looking at something where we have, say, a mixture of two organic solvents, maybe something like maybe we have a mixture of hexane plus benzene or something like that. And we're also looking at the hexane and benzene vapor that is going to be present as well. So at this point we're not considering any point where this solidifies and freezes, but we're only considering the liquid and vapor phases here like this. And what we're going to be looking at is how does how can we predict what if we know, say, the concentration of the liquid, can we predict the concentration of the gas? Is it going to be the same? Is it going to be different? And how could we maybe separate out this mixture? These are the sorts of things that we'll be looking at the thermodynamics of this. Now, before we do that, we're going to be looking from this point on in the class at systems with more than one component. So in this example, maybe we would call hexane component 1 and benzene component 2, something like that. We'll limit ourselves to things with only two components in this chapter. You can, of course, expand this. The same ideas we're going to talk about can be expanded to more components. You could have a 3-component, 4-component mixture, which often is necessary if you're dealing with a very complicated system. But we're going to stick to 2 to understand the principles going on here. Okay, so when we're thinking about a mixture like this, we have this type of quantity we need to think about called a partial molar quantity. And let's discuss what this means and how it is useful for us. The partial molar quantity we're going to be most interested in is the chemical potential, which is a partial molar quantity. It's basically a partial molar Gibbs energy. But this also applies to, say, molar volumes or things like that, which we'll see in just a second. So when we're looking at this component, one of the variables we care about are how many moles of each do we have? How many moles of hexane and benzene do we have in this example that I'm given? And let's think about, for a liquid-liquid mixture like this, before we get to the partial molar quantities, the Gibbs phase rule. So we looked at this. This is the number of degrees of freedom is equal to the number of components plus 2 minus the number of phases. So in this case, our degrees of freedom, we have 2 components. We have 2 that we add, and then we have 2 phases. We have gas phase and liquid phase. So overall, we have 2 degrees of freedom for these liquid-liquid mixtures. What that means is that we can usually think about temperature and pressure. Both T and P can change. And what we'll often do is we'll look at a slice of this where we fix one of these and change the other. But really we're looking at sort of a 3-dimensional plot, but we maybe fix one of these at a time. That's sort of what we'll look at. Okay, so we have temperature, pressure, and then also the number of moles of each of our substances that we have. These are the things that are going to control the Gibbs energy, which is, of course, the variable we care about the most. So we can say that G for our system is going to be a function of a lot of things. G is going to be a function of the temperature and the pressure. Now that's naturally true, but it will also depend on how many moles of each of our substance that we have and which phases they're in too. But for now we're just considered number of moles. So if we want to write out the change in the Gibbs energy, we can write out this total differential as dG, and we're going to have 4 terms, one for each of the variables that we have. So we'll have G changing with respect to temperature, holding everything else constant, so pressure, N1 and N2, multiplied by dt. And then we'll have a similar term for each of the other variables, where we hold everything else constant. So we'll have our pressure term second, dG dP, at constant T, N1 and N2, times dP. We'll have the partial derivative with respect to N1, holding temperature, pressure, and N2 constant, dN1. So that tells us how will G change as we change the number of moles of N1. And then we'll have a final term, dG dN2, holding temperature, pressure, and N1 constant times dN2. Now these partial derivatives here, we saw these when we looked at single component things. These are what we call chemical potential. The only difference here is that instead of thinking about different phases, now we're now thinking about number of moles of particular components. So we could write this one as mu1 and this one here as mu2. That's just our definition of chemical potential. Now, if we have a fixed composition, then these terms go to 0. Well, not the mu values, but the dn1 and dn2 would go to 0. And that would be sort of not that exciting, but we want to think about how as things change. Some other things that we can say here are that these first partial derivatives, the dg dt, constant p, and n1 and n2, this is equal to minus s. We know this from the Maxwell relations. And also dg dp at constant t and constant n1, constant n2, this is equal to v. Now we could write these all as molar values if we wanted to. Okay, and so we can rewrite this total differential here in simpler terms. So dg is equal to minus s dt plus v dp plus chemical potential of substance 1, dn1, plus chemical potential of substance 2, dn2. And this gives us our generic equation for the Gibbs energy. Okay, so in the next video we'll go into, we haven't talked about partial molar quantities yet, but in the next video we'll go into what those are specifically. And we'll look at that in the context of thinking about Gibbs energy and some of these variables here.